Expectation maximization algorithm, EM algorithm. In K-means, we approach the clustering as the problem of finding codebook vectors that minimize the total reconstruction error. In this section, our approach is probabilistic and we look for the component density parameters that maximize the likelihood of the sample. Using the mixture model of equation 7.1, the log likelihood given the sample x equals to the set x to the t for O in xt is that L of phi conditioning on x is equals to log of the multiplications of the probability of x to the t conditioning on phi, where the multiplication is taken among possible t. If we take out part of the component, then we can do the following. It becomes a doubling summation, where the outer summation is summing for O in xt. Then the inner summation is the results of the log of the summations of the probability of x to the t conditioning on gi times the probability of gi, where the summations within the log is for index I starting from 1 to k. Repeat. Includes the probability of gi and also the sufficient statistics of the component densities, the probability of x to the t conditioning on gi. Unfortunately, we cannot solve for the parameters analytically and need to resort to iterative optimization. The expectation maximization EM algorithm is used in maximum likelihood estimation where the problem involves two sets of random variables, of which one x is observable and the other z is hidden. The goal of the algorithm is to find the parameter vector phi that maximizes the likelihood of the observed values of x, L of phi conditioning on x, but in cases where this is not feasible, we associate the extra hidden variable z and express the underlying model using both to maximize the likelihood of the joint distribution of x and z, the complete likelihood LC of phi conditioning on x, z. Since the z values are not observed, we cannot work directly with the complete data likelihood LC. Instead, we work with its expectation given x and the current parameter values phi to the L, where L indexes iteration. This is the expectation E step of the algorithm. Then the maximization M step. We look for new parameter values phi to the L plus 1 that maximize those. Thus, the E step is the expectations of phi conditioning on phi to the L is equal to the expectations of LC of phi conditioning on x, z conditioning on the output of LC is conditioning on x and phi to the L. Then we take the expectation. This is the E step. The M step is we updated the phi to the L plus 1, which is equals to the argument maximum of the expectations of phi conditioning on phi to the L, where the maximum is taken among all possible phi. Now, Tapster, Laird, and Rubin in 1977 proved that an increase in the expectation implies an increase in the incomplete likelihood. That is, L of phi to the L plus 1 conditioning on x is greater than or equals to the expectations of phi to the L conditioning on x. In the case of mixtures, the hidden variables are the sources of observations, namely which observation belongs to which component. If these were given, for example, as class labels in a supervised setting, we would know which parameters to adjust to fit that data point. The EM algorithm works as follows. In the E step, we estimate these labels given our current knowledge of components, and in the M step, we updated our component knowledge given the labels estimated in the E step. These two steps are the same as the two steps of K-means. Calculation of bi to the t in the E step are re-estimation of mi, that is from the M step. We define a vector of indicator variables z to the t equals to the set z1 to the t, z to the t, and so on till zk to the t, where zi to the t is equals to 1 if x to the t belongs to cluster gi and 0 otherwise. Z is a multinomial distribution from k categories with prior probabilities pi I, shorthand for p of gi. Then P of z to the t is equal to the multiplications of pi I to the zi to the t, where the multiplication is taken among all indexes I starting from 1 to k. The likelihood of an observation x to the t is equal to its probability specified by the component that generated it. That is, the probability of x to the t conditioning on z to the t is equal to the multiplications of pi of x to the t to the zi to the t, where the multiplication is by applying for all those index I starting from 1 to k, and the pi of x to the t is shorthand for the probability of x to the t conditioning on gi. The joint density is the probability of x to the t, z to the t of these two variables. The joint density is the probability of z to the t times the probability of x to the t conditioning on z to the t. And the complete data likelihood of the IID sample x is LC of phi conditioning on xz, which is equals to log of the multiplications of the probability of x to the t, z to the t conditioning on phi, where the multiplication is taken among all possible t. And after we take out the multiplication from the log function, there will be the summations summing for all index t of the following term: log of the probability of x to the t, z to the t conditioning on phi, which is, if we expanded the definition, that will be equals to the summations summing for all t of the log of the probability of z to the t conditioning on phi plus the log of the probability of x to the t conditioning on z to the t and phi, which again we can do the expansion from the original term, the first term of the log of the probability of z to the t conditioning on phi to and also the second term. We take out the zi to the t component and do the doubling summation. That is the outer summation summing for index t, the inner summation summing for index I of zi to the t, because z to the t has k dependent components, and for zi to the t we have log pi I time, plus log of probability I of x to the t conditioning on phi. Then after that we multiply with that with zi to the t. Okay, then next we discuss Estep. Estep, we define the expectations of phi conditioning on phi to the L is equals to expectations of log of the probability of xz conditioning on x and phi to the L, which is equals to the expectations of LC of phi conditioning on xz conditioning on x and phi to the L, which is equals to the doubling summation summing with outer summation summing for index t, inner summation summing for index I of the expectations of zi to the t conditioning on x and phi to the L times log pi I plus log of pi of x to the t conditioning on phi to the L, where the expectations of zi to the t conditioning on x phi to the L is equals to the expectations of zi to the t conditioning on x to the t and phi to the L, and where x to the t are IID, which is equals to the probability of zi to the t equals to 1 conditioning on x to the t and phi to the L, where zi to the t is a 0,1 random variable, which is equals to the probability of x to the t conditioning on zi to the t equals to 1 and phi to the L, times the probability of zi to the t equals to 1 conditioning on phi to the L, divided by the probability of x to the t conditioning on phi to the L. This is Bayes' rule, which is equals to the probability pi of x to the t conditioning on phi to the L times pi I divided by the summations of pj times x to the t conditioning on phi to the L times pi j, where the summation is summing for all index j. If we do the simplification, it will be the probability of x to the t conditioning on gi and phi to the L times the probability of gi divided by the summations of the probability of x to the t conditioning on gi phi to the L summing for index j times the probability of gj, which is equals to the probability of gi conditioning on x to the t and phi to the L, which happens to be the definitions of hi to the t. we see that the expected value of the hidden variable, the expectations of zi to the t, is the posterior probability that x to the t is generated by component gi. Because this is a probability, it is between 0 and 1 and is a soft label, as opposed to the 0-1 hard label of k-means. Now the m step, we maximize the expectation to get to the next set of parameter values phi to the l plus 1. Okay, the phi to the l plus 1 is the argument of the maxima of the expectations of phi conditioning on phi to the l, which is equals to the doubling summation where outer summation summing for index t, inner summation summing for index I, of hi to the t times log pi I plus log of pi of x to the t conditioning on phi to the l, which is equals to doubling summation, again summing for all t and summing for all I, of hi to the t times log pi I plus another doubling summation, again summing for all index t and I, of hi to the t times log of pi of x to the t conditioning on phi to the l. The second term is independent of pi I. That's why we isolated them, and using the constraint that the summations pi I summing for index I is equals to 1 as the Lagrangian, we solve for that. Theta pi I times the doubling summation summing for all t and all I of the term hi to the t times log pi I minus lambda of the value, the summation summing for all pi I summing for index I minus 1. Okay, such the difference of these two terms is equals to 0, and we get that pi I is equals to the summations of hi to the t summing for all t divided by n, which is analogous to the calculation of priors in equation 7.2. And similarly, the first term of equation 7.10 is independent of the components and it can be dropped while estimating the parameters of the components. We solve for the delta phi of the doubling summation summing for all t and I of hi to the t times log of pi of x to the t conditioning on phi, which is equals to 0. If we assume Gaussian components pi hat of x to the t conditioning on phi, which is approximately by the normal distributions of MISI, the m step is mi to the l plus 1 is equal to the summations of hi to the t times x to the t summing for all t divided by the summations of hi to the t summing for all t. And the update of si to the l plus 1 is equal to the summations of hi to the t times x to the t minus mi to the l plus 1 times x to the t minus mi to the l plus 1 transpose, summing for index t, then divided by the summations of hi to the t summing for index t. Now, where for Gaussian components in the E step, we calculate hi to the t is equals to pi I times the absolute values of si to the minus 1/2 times exponent of the following, minus 1/2 times x to the t minus mi to the transpose times si to the inverse times x to the t minus mi, divided by the denominator, the summations summing for all j of the term, pi j times the absolute value of sj to the minus 1/2 times the exponential of minus 1/2 times x to the t minus mj to the transpose times sj to the minus 1 times x to the transpose minus mj. And again, the similarity between the equations 7.13 and 7.2 is not accidental. The estimated soft labels hi to the t replace the actual unknown labels ri to the t. EM is initialized by k-means. After a few iterations of k-means, we get the estimates for the centers mi, and using the instances covered by each center, we estimate the si, and the summations of bi to the t summing for index t divided by n give us the pi I. We run EM from that point on as shown in figure 7.4. Just as in a parametric classification, section 5.5, with small samples and large dimensionality, we can regularize by making simplifying assumptions. When pi to the hat of x to the t conditioning on phi is approximately by the normal distribution with parameters mi and s. The case of a shared covariance matrix, equation 7.12 reduces to the minimizations, where the minima is taken among all possible mi and s. And within the minima is the doubling summation summing for all t and I of the term hi to the t of x to the t minus mi to the transpose times s to the inverse times x to the t minus mi, where pi hat of x to the t conditioning on phi, which is approximately by the normal distributions of mi, and s squared times the identity matrix. The case of a shared diagonal matrix, we have the minimization, where the minima is taken among all possible mi and s times the doubling summation summing for all t and all I of the term hi to the t times the square of the difference between x to the t minus mi divided by s squared, which is the reconstruction error we defined in k-means clustering, equation 7.3. The difference is that now hi to the t is equal to the ratio between the exponential of minus 1/2 divided by s squared times the square of h to the t minus mi, and the ratio with the other term on the denominator. That is, the summations summing for all j of the exponent of minus 1 divided by 2 times s squared times the square of h to the t minus mj is a probability between 0 and 1. Bi to the t of k-means clustering makes a hard 0-1 decision, whereas hi to the t is a soft label that assigns the input to a cluster with a certain probability. When hi to the t are used instead of bi to the t, an instance contributes to the update of parameters of all components to each proportional to that probability. This is especially useful if the instance is close to the midpoint between two centers. We thus see that k-means clustering is a special case of EM applied to Gaussian mixtures, where inputs are assumed independent with equal and shared variances. All components have equal priors and labels are hardened. K-means thus pave the input density with the circles, whereas EM is the general case uses ellipses of arbitrary shapes, orientations, and coverage proportions.